Hello and welcome to the Happy Maths Hour. Today it's all about shadows, shadow maths.
We need to be clear about the difference between shadows and silhouettes. So, Caroline, what about this difference here?
Right. So I can see 1, 2, 3 pictures with, well, 2 pictures with very clear silhouettes. Your little itty bitty tricky, well, 3 pictures, but one of them with the silhouettes, the one at the bottom left, has all those lads and lasses where you can absolutely see their silhouettes and they're black, but their shadows are coming towards us, so the light is behind them. So the silhouette is the figures standing up, and the shadows, all we can see of them is the shadows of their legs.
Yes, but what about that very romantic picture? It looks as if he's proposing to her, doesn't it? He's down on his knees.
It does. It looks like she's just in shock because he's just proposed, and I don't see a single shadow in that picture, not even a shadow of the silhouette of the plants. That is 100% silhouettes.
The runners in the picture on the right, you can see shadows, but actually I don't see any silhouettes there.
No, there's no,
the legs are a proper picture of a person's legs.
Yes, you can see the legs, you can see the shoes, you can see the skin tones nearly. They're not silhouettes, they are just shadows, but they're very long shadows. Sun's clearly low down, or either coming up or probably coming up. When it comes to running. And the same with the lady below. She's half a silhouette. The front of her is more of a silhouette. It's like the dark side of the moon, isn't it? We can see half of her lit up from behind her. Well, the front half of her is more of a silhouette. But you can see all of her shadow, again, distorted because it's on a white background, because it's on a curvy white background.
Yes. I mean, I think that's more of a picture of her, and the light effect is because she's dark and light. Yeah, I agree. Now here, I think these are lovely pictures. Now this little boy, the way he's standing with his hands up, it looks as if he's seen his shadow and that's what he's looking at. It might not be true.
He's got his head down. It looks as though he's looking at his shadow. As you say, it might not be true, but it's nice to fancy that he is.
Yes. Now these girls on the right, they're just jumping for joy, aren't they?
And their shadows are so different, really. I mean, they've got some similarities, but because they've got their legs bent, and you look at the shadows from this angle, it looks as though they've got their legs splayed rather than just knee down. It looks like they look a lot longer.
That's true. But what I like about this picture is that you can see the whole shadow because they're up in the air. You can see the whole shadow. Yes.
Feet and all. Yeah, that's right. Not unlike the boy where you can only see it beyond the feet. Yeah.
Yes.
I think that's a brilliant picture.
Now, one application of this idea of shadows is the sundial, which is used as a clock. And there's a little bit of maths in here in the working out. If you're, I'm sure a lot of you listening to this program know all about Roman numerals, but for anybody who doesn't, it's quite easy to look at this clock and work out how the Roman numerals work, because it starts at 1, just below the center on the right, and you can see it goes 2, 3, 4, and instead of 5 strokes, it's a V. So V is obviously 5, and then it's 5 and 1, which is 6, and 5 and 2, which is 7. It goes along to 5 and 4, which is 9, and then it doesn't have double V, which you might expect. It has, well, you could almost regard an X as a double V, but one upside down.
Oh, I never thought about that. I wonder if that's what it's meant to be.
No, it could have been invented like that. So X is 10, and then you go around. Now you see, as I said, it doesn't have VV, but it does have XV. So that's 15.
Yeah.
And then it goes round to XX.
And again, 20 is not a new symbol. It's just XX, yeah.
Yes, and then XX1, XX, so 21, 22, 23, and the last one's 24.
And just to finish off the conversation about Roman numerals, for those that don't remember, when you get to 50, then it changes to L, and then when you get to 100, you have the century, the source of the cent, the century, centurion. It was people. I think it was 100 people in the group, and so the C is cent, century, 100.
Now, what is a great project is to make your own sundial, and if you make it with these right sort of materials, you could make one for your garden actually, and keep it as a permanent feature. And you
what a great activity for children to do, to make their own sundial.
And you need to calibrate it, which means you need to start at noon when the sun is directly overhead, and then for each hour of the day you need to use a clock to calibrate it, but after then you can put your clock away and your sundial will tell you the time. Provided the sun's shining.
Provided the sun shines. Sometimes there is a vague shadow, even if the sun's not shining, it's just a little bit of a shadow. But what I've never quite understood, Tony, is how you work out for the different times of year. Or is it because the sun's not always in the same place at noon, at least not in the...
it won't do daylight saving time. It'll be an hour out.
Sure. Yeah. Oh, the sundial's just adjusted itself to daylight savings time.
Well,
does it? I mean, if you set it at midday, say daylight savings, does it stay? Is midday always in the same place? I've always wondered that.
But you see, the sun won't be directly overhead unless it's the proper Greenwich Mean Time noon.
Yeah.
So I
think it's a lot easier to do at the equator than anywhere else.
No, you can do, well, sunny there, but you can do it as long as you do it at Greenwich Mean Time noon, and the sun should be directly over. Well, you're right about it being perfectly directly overhead at the equator. Yeah. But there are lots and lots of sundials in this country that are pretty good when it comes to looking at what the time is.
I think it's an exercise that everyone participating will learn from, and it's certainly one I would learn from if I make a sundial.
Now here you see on the right, you see a sundial, and what you see is an arc, and you can imagine the sun has come across, and in the blue side there was, it was before sunrise, and then it's come across to where it is now. And you can see the gnomon, it's called. That's the thing that casts a shadow. You can see it moving round. Would you like to do it again, Caroline? I think that's rather nice to watch that. Now watch the gnomon moving and the shadow moving as the sun goes across the sky.
So due north is 12 o'clock. That's how it works. Somehow. I'm not sure, but I definitely think that's a worthwhile exercise to do, to learn how it does work. What better way to learn how it works than to actually make one and adjust it until you're successful with it. Wonderful.
The other thing is quite fun to do is when you're out and about to keep a lookout for sundials, because there are different sorts. And have a look at them closely and see how they're designed and the differences between one and another. So shall we move on then? So now here we're on to the shadows in, well, this is a question to work on some geometry, but on the right you see that you can have a lot of fun and we're creating shadow pictures on the wall with your hands. And you see a bird there, but you can make fox faces and all sorts. Now here we've got in the picture there, we've got a circle, a square, a triangle, and a rectangle. And the question is, if that's the 3D shapes, what 3D shapes could have made those images, those shadows?
So they're shadows. What 3D shape would make a 3D shape to make the shadow? Well, a cone could have made the circle, couldn't it? Or a cone on its side could make the triangle.
Yes, that's right. So one shape could make more than one of these shadows. And similarly, the disc there could be the shadow of a cylinder or a ball.
Or a sphere. And the rectangle could also be the shadow of a cylinder that's lying on its side.
There are lots of possibilities. And of course you can do it. This answers the same question for flat two-dimensional shapes. And you can even get a two-dimensional shape to give you a line by moving it round so that it's perpendicular to the screen.
Yeah.
Just show you a line. And you're sort of living in flatland. Yeah, but I think that's a really good little activity. And if you've got a group of people, they will see different things. They will come up with different suggestions, and you can have a lively discussion about what objects could make those shadows. So I do recommend that to you. It's a really nice thing to do.
I mean, it's a fantastic visualization activity. And if you can only visualize 2 or 3 things, you've already utilized your visualization skills and improved them. And then you can extend that to see, well, what different people make different suggestions, and that it'll stretch your imagination because you'll realize there are other shapes that make them as well. And I think it really exercises your imagination beautifully.
Now you can have a cube, and you can obviously cast a shadow, which is a square as you see it, but you can make a hexagon shadow from the cube. Try it. And also you can make a rectangle. You can see the rectangle on the right. Okay, so you can do all those things with a cube, perhaps more. You try it and see what shapes you can find.
Yeah, and see what, and with lots of different shapes, see what shapes you can make, especially your normal, the 3D shapes you're used to playing with. Be surprised what you can come up with shadows.
You know, if you're at home, go around your house and find a few objects that are sort of solid and small enough to use for this purpose. But it could be something like a coffee mug, but anything that's, you can cast a shadow with, and experiment and see all the different shapes that you can make with that one object. And it's really quite interesting. I mean, it's similar to the little puzzle of, you show photographs from different directions, and sometimes it's hard to believe that you're showing the photograph of the same object. So this exercise is a little bit similar to what I've just described. So you can have a lot of fun making shadows, and you can be very creative with it too, with making shadows of animals and all sorts with your hands or other objects. Okay. Now here we're going to think about shears. Now this is a very important topic, because if you imagine a skyscraper, okay, it shears. It actually moves. If there's a high wind, it moves ever so slightly, all from the direction of the wind makes the whole skyscraper move a little bit, and that is a shear. Okay, now it doesn't change its volume, And when the wind dies down, it will go vertical again, and it's so slight that nobody notices a difference. But nevertheless, buildings like that have to be built so that they can stand up to a certain amount of shearing force.
And that's when there's wind, and then also there's earthquakes.
Absolutely. So if you take a place like San Francisco, which is prone to have earthquakes, the building is designed, the engineers structural engineers have to plan how to build the building in such a way that it will not just shear, but shiver rather, because and move because of the earthquake. And nevertheless, it won't crack and crumble. It will retain its overall shape and return, once the earthquake has passed, it will return to how it was before. And so what we say about a shear is that it's a change in shape if it's a 2D shape with no change in area, and if it's a 3D shape with no change in volume.
Okay, all right.
Now, what it means for my diagram there of the shadow of a triangle, there's two white lines in the middle, and they are the same length. And for a shear, they will remain, when you shear it, that slice in the direction of the shear. Oh, the shear is in the direction of those blue dotted lines. It's
so you mean it stays within those two parallel lines?
Yes, that's right. And also notice that the base of the triangle doesn't change. The base is the same.
Right. So the length of the base stays the same. It's the position of the apex, let's say, that moves, that changes.
Yes. And we know the formula that the area of a triangle is half the base times the height. So if the length of the base stays the same and the height stays the same, then it will be a shear. Now, if I had drawn my white lines across it higher up, they would have got shorter, but they'd on the two views, the shadow and the shear, they would be those white lines would be the same length. If they're at the same horizontal level, they'll be at the same length.
Yes. Yeah. Okay. Yes. So you can see that the height doesn't change. Therefore, the area, the base doesn't change. The height doesn't change. Therefore, the area doesn't change. So we can see that.
Yes. And these horizontal slices are where they slice through each of those two shapes. The horizontal, if they're on the same horizontal level, the horizontal slice is the same.
Right. Width. So that width doesn't change either. Okay.
Yeah. And as you go up, those horizontal lines, as you go up, they get shorter and shorter to 0 at the top at the vertex.
But the width or the length of that line at whatever height is the same on the shears one and the original one.
Yes, on the two.
What changes is the angle at the base. Then.
Yes, the angles
apex
change.
And the base. The angles change. No, that's it. The angles change.
Yes. Yeah. Now on the right, those shadows, you can make the shadow with an equilateral triangle. It looks like any of those shadows, but they're not shears. But can you see that the base has changed, and
the first two, the base has changed, and the third one, the height is different.
Yes. Yeah. So let's look at that with another object. So as in we look at a disc, and we do it with a disc. Okay. Now here, there's two there's a shadow and a shear of the disc. Now the shadow is exactly the same size, and I put a white line across it because we want to talk about the length of the white line.
So again, the length of that white line is that as long as that's the same, then the one on the right is a shear of the one on the left, and the height as long as it stays within the parallel lines.
Yes,
as long as it touches the parallel lines.
But what's interesting here is the top half shears in one direction, and the bottom half shears in the other direction.
Right. Yes, so it does. Yeah.
Which is perfectly possible for geometrical shear. It's not going to happen. We hope it's not going to happen with a building.
Yes, quite. Yeah, that would be quite unstable, one would imagine.
I don't think it would go back to where it was originally.
I think it would change its center of gravity quite dramatically.
Unfortunately, I think that wasn't there a building in Miami, that a big, tall building that collapsed recently, only a few months ago.
There was one, yeah.
Yes, and whether that was wind or a hurricane, I'm not sure. But the engineers didn't do their job adequately there, because the building should never have collapsed like that. It was a real tragedy. Yeah. And so here is a shadow of the disc, but this is not a shear.
Right. It's got a different area. Yeah.
Yes, and it's the light must have been very much lower down to cast a shadow like that.
Yeah.
Okay, now here we come to another challenging question for you, and you could spend a long time answering this one, because there's lots of different possibilities, especially when you get to the shapes that have got more faces, like the octahedron and the icosahedron. So here the question is, what shadows can you make with these 3D objects? They're the regular polyhedra. So the regular polyhedra are polyhedra where all the faces are the same, exactly congruent of the same polygon, and all the angles everywhere are equal. And there are only 5 solid objects, polyhedra, for which that is true.
Mm-hmm.
So let's just think about that. So supposing we cast there's the tetrahedron, okay, triangular base pyramid, if you like, and there, imagine its shadow. Now then, imagine what would happen if you cast a shadow with a light. Now that light has got to go straight down, perpendicular to one face, through the opposite vertex.
Oops.
Yes. So let's just look at what we've got here. There's another possible image, and then Caroline's going to show you a few that she's going to demonstrate casting some shadows.
I was getting it ready, and then I flashed it by mistake.
And here on the right, you'll see I put some lines in it, so you can see how this quadrilateral is in fact a shadow of the tetrahedron. You can see, because of that one face outlined in orange, and you can see the other triangles there, 4 triangles. So if you look at it, you can see it is a tetrahedron, but the orange lines and yellow line are just to help you to see it. It's the shadow of a tetrahedron.
The tetrahedron being a triangular base pyramid.
Yes. So
all the faces are triangle. Whoops.
What you can get from your regular tetrahedron is an equilateral triangle, and as the light source moves, the shadow changes to other triangles and to quadrilaterals. So you can experiment yourself with these. So let's look at some shadows, and then Caroline is going to demonstrate some, and you can imagine you can do it yourself, and it's quite fun to do. But you need to spend, if you're going to find all the answers to this question about these 5 solids, 5 polyhedra, and all the types of shadows you can make, I'm not guaranteeing. I've told you all the possibilities for a tetrahedron, let alone for the other shapes. Now, here's a shadow of a tetrahedron. Okay, and this is a skeleton of a tetrahedron. Not like a skeleton like the little girl's skeleton you saw, but this is just the bones, actually. It's actually those sticks are the edges of the tetrahedron. And there's some more shadows. Would you like to talk about them? Because you had some children at a workshop last week, and they made these shadows, didn't they?
Yeah, the first one on the left, the tetrahedron, which is 4 triangles, is sitting on a piece of paper, and it had a light source coming from quite low down, so it was like a low sunset, and the child wanted to actually draw the outline from that angle, so he took the shadow and then drew a 3D representation, 2D representation of the shadow. So he used the shadow to draw it on 2D as you would in your imagination, but he actually did it using the shadow.
And the outline is a hexagon, of course.
I'm talking about the first one on the left, going back to the tetrahedron.
Oh, the tetrahedron.
So the outline of that one is a triangle, but it's a lot longer than the tetrahedron itself. The top left, the middle one at the top, it is a cube. So if you look at the bottom one, you can see a red cube that's been held with 2 hands, and the shadow, his attempt was to make it into a square. So he managed to line it up. The light source was behind him. He managed to line it up into a square. And then the challenge was, can you make a hexahedron, a shape with 6 sides? And if you see the one on the top right, that was the first attempt, which was a very credible attempt. And he managed it. He's like, oh, I have made, because first he was saying it was a pentagon, it was different things. And then he realized, no, it does have 6 sides. It is a hexagon. And then I challenged him to make it out of triangles and only triangles. So he noticed all the different shapes, and then he made the one on the left, which is 6 triangles, making up pretty much, they're not quite identical, but they can be made to be if you get it at the right angle and the light source right. And so you can make and that shape, the cube on the bottom right, the shadow of that cube is making a hexagon made out of 6 triangles.
Well, at the bottom there, with the colourful wall in the picture, you can see that the square shadow is made just with a cube.
Yeah, that's what we first started talking about, is that one.
Yeah.
Because that was the first challenge, was to make a cube. And so he had to position it just right so that the light would go straight through it.
So suppose you had a solid shape rather than a skeleton, then you could do something like this. So there you see in the top picture, there's a cube, and it's a cube with some photographs in it, which just stands on my windowsill, and it's very faded and you can't really see the photographs. But nevertheless, it is a cube, and you can see that the shadow there, well, and the one below are more like a rectangle than a square, aren't they?
But the second one does look more like a square, and the first one is very definitely a rectangle.
Yes, and the bottom one is a hexagon.
It certainly is, and it's just because the angle that you're tilting it to create the shadow. It blew me away the first time I saw a hexagonal shadow made from a cube.
But Caroline, I don't think that looks quite regular to me. I think some of the edges are shorter than others.
Definitely, very definitely. The bottom one and the next one along the left, that's much longer than the one on the top. So that's going back to the little cube that you draw when you're at school, making got the diagonals shorter than the face and things. They're definitely not a regular one there, but you can make it regular if you hold it just right. And it's lovely playing with it.
So do you want to do some demonstrations? Yep. So you see the tetrahedron sitting on the white background there, and Caroline is going to move it around, and you can see the shadow behind it. So Caroline, can you tilt it even more. Keep tilting it. Yes, now we can see both the object. That's a bit better. Hold it still, Caroline. So now we can see the object and its shadow. You can now move it and show us a few more, viewed from a few more directions, Caroline. I wonder if you can make just a triangle, Caroline. Can you? Yes. There. Wow. That shadow is just a triangle. Well done. So, what else do you want to show us, Caroline? Yes. So we have lots of different views of the tetrahedron here. And now you can see that some of them you actually see not just a triangle, but the edge, the outer edge is a quadrilateral. So if it was a solid tetrahedron, you would see a solid quadrilateral, and you would have to work out where the edges were. You wouldn't necessarily see you wouldn't see the edges. That's fantastic, Caroline. Really good. Are you going to show us a cube? Yes, here we go. Here's a cube and its shadow. That's the red cube. I think it's the same one you've seen on my slide. Now, can you make a shadow into a square? There we go. Almost a square. You see two edges on the left on one side. You have to be careful, Caroline, not to get in the way of the light yourself. Okay. What else can we see? Can you make a hexagon for us, Caroline? Yes. Now, we have a little tiny square in the middle, and I'd like to see that. Oh, there we go. There's a regular hexagon with made up of 6 equilateral triangles. But as you see, it is a cube that's making those shadows. So there's lots of possibilities there. And now Caroline's turning it round, so she makes a square, but then a rectangle. Or no, it's got 4. Yes, she can make a rectangle, I think. Yes. I know she can make a rectangle. Great. Now Caroline's going to do something with this. This is not regular. This is not one of the things we asked about, but this is a prism. It's a triangular prism. Okay, so you can do all sorts of interesting things with this. So it's like, the typical roof of a house and with the loft inside. Attic inside. Okay. And this is an octahedron. Now that is one of the regular shapes. That's got 4 faces, which, what am I saying? 8 faces that are equilateral triangles. And we can see, you might be able to make a square with that as well, Caroline. Can you make a square? Yes, there you go. By lining up with 2 of the vertices, one behind the other, she's made a square. And actually, the regular octahedron, you can think of it as 2 square-based pyramids glued together in the middle. So it's got a plane of symmetry there in the middle, which is a square. Caroline often makes these, children make them out of 4 squares. How can you make 4 squares into? Oh, that's a nice, because you've got what you've got there That's lovely, Caroline. She's got a star there. Yes, a 6-pointed star. There's really a lot of scope here. Now, here we see that the squares are, the square cross sections are now distorted into parallelograms. And there, the outline is a rectangle now. On the outside is a rectangle. So if we did that with a solid octahedron, we'd be seeing a rectangle now. So Caroline's shown us a shadow which is a square, and she's shown us a shadow which is a rectangle. Now Caroline's got a solid. Now this is a solid tetrahedron, and now you can see what I mean. You only see like the shapes on the right on the on the PowerPoint you just saw. Now she's made it. The shadow is a quadrilateral there. This is not solid octahedron. Yeah, solid octahedron. And so Caroline's making a rectangle, a rectangular shadow. Triangular shadow. Square shadow. Yes. Solid cube. At least I think it's a solid cube.
The small shapes just didn't work to make a hexagon. Couldn't make them happen.
Well, it was really good what you showed us, but it just opens up the whole question, really. It opens up the question of what shapes can you make? And I'm sure if other people want to try it, they'll find a lot of answers, and it's great because different people will find different shadows. Now here
what I found, Tony, when we were doing it, was it gave huge insights into the shape. So when you're looking at a shape, even when you're turning it around or even making the shape, you get some insights. But when you do make shadows with it, whether it be the skeleton or solids, then you get other insights. You get some amazing surprises. It really worked very well. It was a wonderful exercise. I want to do it again.
Now here we're moving to something slightly different. So we're looking to look at congruence and symmetry now. But you can see the little man on the left there. Now he was just made with some scrap card. And there he is. I folded it and cut him out, and there he is sitting down, holding his arms out, and you can see his shadow, and the shadow of his head and the shadow of his arms. Now he is absolutely symmetrical, like the little dolls on the right. The little men as well are congruent. The three little men are congruent to each other. So I've concertinaed the paper there before I'd cut out those little men and then open them out. I did it very carefully so they were holding hands. And it's a lovely thing to do if you haven't done it before, to make different paper dolls all holding hands in a long line. And if they are, because you cut them that way, so I did 3 at the same time there, they are what we call congruent. Now in mathematics, the word congruent means they're exactly the same size, exactly the same shape, all the lengths are the same, all the angles are the same, right? And you could put one on top of the other, and you could see that they matched exactly. That's what congruence means. Now the symmetry in these little dolls is shown there because that was where the paper was folded. So the doll is exactly the same on the left and the right. Now we're pretty much the same on the left and the right. Our eyes and our ears, we've got 2 of those. And because they're in the middle of our faces, we've only got 1 nose and 1 mouth. but we've got 2 arms and, you know, the rest of it. Now, we're not perfectly symmetrical. A very sort of a fun project is to take a picture of maybe of yourself, a selfie, and then and then crop it so that you have an image, okay, of the, let's say, the right-hand side of your face, and then flip that and put the two together and see if this perfectly symmetrical you looks the same as you look or a little bit different. So, for example, if you part your hair exactly in the middle, or have no parting at all, it may look pretty much the same, but probably you'll be surprised at the difference.
It doesn't. You look bizarre, even if your hair isn't switched over, or
yeah,
as long as, even if your hair's symmetrical, it isn't. There's
but
very
if you
few. Greta Garbo supposedly had a perfectly symmetrical face. If you look at my face, you can see this eyebrow sticks up over my glasses, and this eyebrow's down behind my glasses.
I never noticed.
I have a quizzical expression on my face at all times because one eyebrow's way higher than the other. And even your 2 nostrils are different.
And you see, if you have a parting in your hair on one side, and you do what I have described, you'll see no parting, or you'll see two partings.
And that's something really obviously weird.
Yes.
But if you manage to do it without, or just the face, just remove the hair completely and just the face, it looks totally different. It looks unfamiliar. If you have 2 identical, only half of your face mirrored, it's not you.
So, you know, playing games like that aside, symmetry is a very important concept in mathematics, which we begin to learn about in school, as is congruence. And here you see we're back to Halloween. We've got, because these were done and all cut out at the same time, the orange pumpkin faces are all the same as each other, and the grey pumpkin faces are all the same. So they are congruent. Now then, the next idea is to look at similarity. So how do you like Pooh Bear? Everybody loves Pooh Bear.
The only thing I like better than Pooh Bear is Pooh Bear in a Tigger onesie.
And you've got both there, all right?
I have Pooh Bear in a Tigger onesie. My life is complete.
Now, similarity means something different in mathematics to what it does in the real, everyday English. Similarity means that all the angles are the same. Absolutely. All the angles must be the same. And when you talk about something being similar, it's a much vaguer description, isn't it, in everyday English? So don't believe that similarity, or talking about 2 diagrams or pictures that are similar, when it's mathematics. It means much more than it does in everyday, sort of common talk. Now, this is how films are projected onto a screen at the cinema. And so you may see a Winnie the Pooh film with a huge Winnie and Eeyore and the rest of them, but that's projected from only a very small image way back, and the projector does this sort of thing. So the same point, if you look at Pooh Bear's nose, right? And the light source is just above the E in cinema there. And you've got to imagine that those dotted lines are show you some rays of light, which is giving you that projection, or rather 3 projected images of Pooh Bear. Now here you can see the light. Now there's a point source of that energy, and you can fix something up like this with a table lamp and a piece of paper and a hole in the paper, and you can cast shadows on your wall. And here you see angle at X, well, X, Y, Z, and x dash y dash z dash are similar. And x dash y dash z dash is an image of x, y, z.
So looking at a triangle, the angles are the same, but the dimensions are different, but the proportion is the same then?
Yes, exactly. So what you see is that there's no distortion in the image, because if you change the angles, then your Pooh Bear wouldn't look exactly like Pooh Bear. He'd look like a squishy Pooh Bear. A wonky Pooh Bear, yes. So that's similarity. I just love these little people.
Yeah, me too. It's a fantastic image.
Now they are similar, and you can see the yellow one. No, the little one, the blue one. You can imagine enlarging him to be the same as the green one, and then enlarging him a bit more, and he's going to be similar to the yellow, and a bit more, and he's going to be similar to the orange one.
So they're enlargements, they're scale models, though.
Yes, they are indeed, and they're all holding their left ear. I can't quite.
They are, aren't they? They're a bit puzzled about something.
I think they're thinking about what they're seeing.
Well, just like Pooh Bear. Think.
Yes, and I put this in because I wanted to now think about magnification. And if you wear glasses, this is quite important. How do the glasses, the spectacles, work? Okay. Now, there are two types of lenses. One's called convex, and that's the one at the top.
Now, so that bows outwards.
Yes. And so there's the fly quite close to the lens, and the large image of a fly is because the eye sees the beam of light, which are not the light. Once it's been bent by the lens, it's not a dotted line, it's a continuous line. And what the brain does, it sort of extrapolates, and it imagines that light, because light travels in a straight line, doesn't it? Mm-hmm. And the brain doesn't think, oh, that can't be right, this lens bent the light. The brain actually thinks that the light traveled in a straight line from the fly to the eye, and therefore the brain thinks that the fly was much bigger, or at least the image that the brain sees is much bigger than the real fly.
So my glasses that mean I can see up close, would they be concave or convex? I would have thought they'd be the convex ones, because I have to say my hand looks bigger than it actually is if I'm looking at it from this distance.
Yes, yeah, I think so. Now the concave lens is different. Here, the light is bent outwards rather than inwards, and what the person sees is, again, that he or she imagines that light traveled in a straight line, and therefore the image they see is a smaller fly than the real one. And
our brains just they allow perception to. Our brains can be easily fooled.
Yeah, and so here's another picture, which it's the light bulb here, which is the object for both types of lens, right? The convex lens makes the light go outwards, spreads the light, and you see the image is bigger. And the concave lens makes the light sort of close, the two beams sort of close down a bit, and you see the image is smaller than the real thing. So I think that's quite interesting. So this is the way lenses work. But in every case, you get similarity.
Oh, okay. So that's the connection. They are similar.
Yes.
So the perception's different. We perceive them to be larger or smaller, but they are similar. So it doesn't So they're still the same shape, just
and they're not distorted.
They're not distorted.
Now, in the geometry here this is about tessellations. What you can see here is some enlargements of the well, you could call it a trionymo because it's got 3 squares, or you could call it a tri-square. And there you see a tiling which is made up of lots of those shapes fitted together. And you can see how you're using this idea of enlargement, which I think is a nice
so
picture.
You're making a larger shape from similar, smaller shapes.
Exactly.
Right. Yeah.
You can look at these links. The shadows activity we've shown you today. The one I've just shown you on tri-squares, I would have a look at that, because that is the tiling one I've just shown you. There's many more ideas there on that activity on the Aiming High website. And then there's 2 more there. Enlargement is more of an exploration of scale and making things larger, and what is the scale between this image, this picture, and this picture? What's the scale? That's very important in real life, isn't it, for map reading and that sort of thing.
The links are all in the description.
So it's goodbye from us. The hour is up.
Thank you very much. We'll see you next week, or we'll see you on YouTube. Have a wonderful week.
Goodbye, everybody.
For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest activities.